Hello everyone, myself Dr. Naresh Sarkar, Assistant Professor, Department of Physics, Shri Shivaji Science College, Amravati. I welcome you all in the lecture series Nanomaterial Synthesis and its Characterization. And today I am going to discuss on the topic Fundamental of X-ray diffraction and instrumentation. Friends, this lecture is totally depends on X-ray and its diffraction and how it is scattering. There are so many fundamental things would like to discuss throughout this lecture. So these are the contents I am going to explain. So what is X-ray and diffraction of X-ray by the crystal, Bragg's principles, then what is Thomson scattering, then constructive and destructive interference pattern, then type of the X-ray diffraction methods, then X-ray diffraction pattern, and on this X-ray diffraction pattern we get the intensity versus 2 theta versus intensity, and some peaks and some curves and the behaviors of peaks and the position of peaks, intensity of peaks and the width of peaks, and sometime when you synthesize your material by varying the value of x, you get the number of XRD results with shifting some peaks towards lower angle to higher angle. That point also I am discuss in this video lecture. So let me continue. As this lecture is based on X-ray, so I would like to say something about X-ray. What is X-ray? X-ray is nothing but a on part of the electromagnetic radiation, and when this electromagnetic radiation is bombardment with the metal specimen, when high energy electron when is bombarded or scattering with the specimen, then there is a numbers of waves that are back scattered and secondary electron scattering, the number of scattering that is happening. So out of this scattering rays, one of the ray which is coming out from the specimen, which I called here, it is a X-ray. According to the Moseley's law, every element has its unique signature in the form of K alpha emissions. Friend, there are characteristics X-ray and continuous X-ray which is coming out from the specimen. X-ray diffraction pattern, we generally use the characteristics X-ray to scatter the atoms or your material, because this characteristic X-ray having the monochromatic wavelength, and that monochromatic X-ray is created by bombarding by using some target material that may be copper, molybdenum, cobalt, nickel, so many. Okay, so this is the brief introduction about the X-ray. So what happened when we use the visible light? You know, the wavelength of the visible light is larger as compared to the wavelength of X-ray. So suppose I have a grating and this is the visible light. That light is coming from these sources. So if this light is passing through the slit with the parallel rays, and when it is passes through the optical grating, then this light get the zeroth order diffraction, first order diffraction toward the each side of the zeroth order, and the second order and third order reflection. But if I use, instead of the visible light, if I use the X-ray source, then this X-ray is not diffracted from this optical grating. Why? The question is why? Because the wavelength of X-ray is too small as compared to the width of the, or the gap between the two lines in the grating is larger as compared to the wavelength of the X-ray. That is why X-ray is simply pass through the grating, but it is not diffracted. So that time people they are try to diffract the X-ray. So that is why the people use the crystal to diffract the X-ray, because as like the optical grating, there is also periodicity, and also in the crystal there is a periodicity of atoms, because atoms are regularly arranged in a three-dimensional, as like the lines which are periodically arranged in a grating. So as like the grating, there is a atoms which are also the periodically arranged. But there is a one thing you have to keep it in mind: interatomic distance, the atom to atom, the distance between atom to atom is in the range of angstrom unit. So if it is in the range of angstrom unit, that means there is a wavelength which is also in the range of angstrom unit, they are capable to scattered through this atom, because the interatomic distance and the electromagnetic waves or the light which is coming from the sources having the wavelength is equivalent or in the order of the wavelength of the crystal. So in general, the interatomic distance of a crystal is maximum 3 angstrom. So that means we need the light or electromagnetic wave not more than 3 angstrom. If it is not more than 3 angstrom, then only this X-ray or that electromagnetic waves are penetrated inside the crystal, and which is scattered from the various atom of the crystal, and it will form the diffraction, and that diffraction is recorded in the photographic plate. Okay, so here in this diagram, this is the X-ray source, and this X-ray source when pass through this crystal, then and only then this X-ray get diffracted, and that diffraction produce a diffraction pattern in the photographic plate. That we will understand in the later part of this video. So that is why people, they are used to study about the X-ray diffraction. Okay, so X-ray diffraction gives some idea about the structure of solid, because we are interested to know about the structure of solid. If you change the structure of material, that material can change the physical, chemical as well as electrical property. So that is why you must know about your material. You must familiar with your material by using the structural data only, because this is the only way to familiar with material in the context of magnetic, in the context of chemical, physical, so many parameters which is depends on the bond length, bond angle, then the strain, stress between the bonds. So if you wanted to know about your material, then you must know about the structure of your material. So that X-ray diffractions will provide the information about the structure of the solid, as well as it is help to study the X-ray spectroscopy. But the structure of solid and the study of X-ray spectroscopy, these two are working on the principle that can follow the principle of Bragg's condition. So this is one of the key parameters of Bragg's condition. The invention of Bragg's law gives an era in the field of crystallography. So this is the real machine. This is photograph indicating the real machine. So this machine contains a source of X-ray, and this is the X-ray detector, and here this is actually the sample holder. On the sample holder we put the material which is synthesis in a laboratory in the form of solid. In case I can say it is not in the form of only solid, but in the form of very very fine powder. So you may put this fine powder or place this fine powder in a sample holder, and you pass the X-ray sources from this sample holder, and they are get reflected or scattered from this material, and that scattered beam is recorded by this recorder, or this is called as X-ray detector. So friends, we may go through a real life example. When you synthesize your material, that material looks like a powder form. If you zoom this powder form material, or this material consists of individual particles. Okay, this is the very very fine powder, and this fine powder consists of individual particle. And if you zoom one of this individual particle, then you can find these individual particles consist of large number of atoms, and these atoms here, it is a periodically arranged. If this atom it is a periodically arranged, then you may say this atom is a crystalline. Otherwise, if it is not, then you may say your material is amorphous or non-crystalline. So once you put this material or this powder form in a sample holder, and you can pass the X-ray sources, X-ray beam throughout the sample, then what happened? This sample is actually in the form of crystalline nature. So there is a periodic arrangements of these atoms. So this X-ray sources is coming from the X-ray machine, and these X-ray sources are incident on this atom. If the X-ray source is incident on this atom, then there is a very interesting thing is happening. So I can zoom this atom here, and this is the zooming image of this phenomenon. and this is the incident X-ray source, which is X-ray beam, which is coming from the X-ray source of X-ray machine, and which is scattered with this atom. Once this X-ray source is incident in a atom, then this atom, then the electrons of these atoms get absorb this energy, and it can be vibrate or it can be oscillate with the frequency of incident beam. Why it is vibrating with the frequency of this with the same frequency of this frequency of incident beam? Because this is actually electromagnetic waves, even though it is X-ray, but it is actually electromagnetic waves. On these electromagnetic waves, the electric field and magnetic field both are perpendicular to each other, and this electric field are oscillating. So when this electric field are oscillating, and this electric field incident on the electron, then this electron also get oscillating frequency, the frequency of this incident beam. So but this X-ray is not having the sufficient energy to remove the electron from its orbiter, such that these electrons are absorb the energy, and this electron get vibrate or oscillated with its mean position, and after a certain time this electron release this energy. This process is called as scattering, and this scattering is also well known for the Thomson scattering, and which is also called as elastic scattering. That means this is the initial X-ray source, and this is the secondary X-ray source. Means when the X-ray source or X-ray beam is incident on the atom, then the atoms of the crystals is also created a new source of X-ray, because the frequency and the wavelength of the scattered beam or scattered ray is exactly equal to the incident ray. Okay, so that means this first incident ray, it is the primary source of X-ray, and the second is scattered ray, which is scattered from the atom in the random direction, which is the secondary, you can say secondary source of X-ray. Okay. So this entire phenomenon mechanism which is happening inside this crystal, and this angle of incident is also play a very important role. At some particular angle, this incident beam get scattered coherently with this first ray, second ray, third ray, fourth ray, and n numbers of rays. That means that crust to crust and trough to trough get match. So when crust and trough they are get match, means there is this path difference. If I say it is a lambda, then this path difference is lambda by 2. That means this trough to trough and crust to crust get match. So if this is get match with n numbers of X-rays, scattered X-ray from the atom, then this beam get reinforcement and produce a high intense, high energetic output X-ray source. This phenomenon is a constructive interference phenomenon. So when it is a coherent and constructive interference, then only we can record it that is as a X-ray diffraction pattern. If not, that means the path difference is lambda by 2. That means this trough and crust are opposite to each other, then they are cancel out each other. That means these waves get automatically destroyed. This destroy of these waves is called as destruction interference. So when it is get destruction interference, that means that time no X-ray diffraction is recorded. Okay. So you should keep it in mind कि only constructive coherent interference is recorded by the X-ray detector, and rest is not recorded because of destructive interference, because there is no waves are created in the output, like this figure shows. This is the constructive interference figure, and this is the destructive interference figure. See, they are cancel out each other, but they produce a new reinforcement or high energy or high intense beam. So there is one more thing that is I would like to share with you, that this condition is happen only when they follow the Bragg's equation. What is this Bragg's equation? That equation is 2d sine theta is equal to n lambda. So friend, if you observe from this area to this area and this area to this area. So these two wavelength are length and everything get equal, but only this path different, f to g and g to h. This path difference are get different from this. If I taking this part of this line and taking this part of this line, then there is a path difference. So what is actually that path difference? That path difference is actually a Bragg's law. Means this path difference is equal to the integral multiple of wavelength. So if this is the one atom of the first layer and this is this another atom of the second layer, then this is the interatomic distance. If it is an interatomic distance, then I may say this distance is d. And if I take a normal, right, if I take a normal from this wave to this atom, then they are creating a theta. If this is theta and this is the d, so by applying this trigonometric formula, we get opposite angle of this theta. That means f to g is a d sine of theta. Means this from f to g, you may say it is a d sine theta, and g to h, which is also called as d sine theta. So what is path difference? Path difference is fg plus gh is equal to the integral multiple of wavelength lambda. So I know the value of fg, which is d sine theta, and I know the value of gh, which is again d sine theta. So this plus this, nothing but a d sine theta plus d sine theta, which is makes a 2d sine theta, and this 2d sine theta is nothing but a path difference, and which is equal to the integral multiple of wavelength lambda. And this famous equation is known for Bragg's equation. And whenever this Bragg's equation is satisfied inside this crystal structure, then and only then there is a constructive interference pattern is produced. And when this constructive interference pattern is produced, that means this scattered beam form a phenomenon. That phenomenon is called as diffraction of X-ray, or which is well known for X-ray diffraction. And this X-ray diffraction creates a XRD pattern. So out of this XRD pattern, you may study the so many things like A value, B value, C value, axis, then HKL value, planes, etc. So this on the basis of this Bragg's equation, so X-ray diffraction can be done by performing three experiments: Levi's experiment, rotating crystal method, and powder methods. This part I will discuss very shortly, because if I discuss Levi's technique, then rotating crystal technique, then it will take more than 1.5 hour. So due to this lack of time, I would like to simple with some key point. Levi's technique gives an idea about not only the crystal, but it is gives the idea about the orientation or symmetry of atom, symmetry of a crystal. So it is not sufficient to know about the shape of your crystal, because if you know the symmetry and orientation, so it is not the sufficient data to describe your structure of the crystal. So Levi's technique gives the orientation and symmetry of the crystal. So in this experiment we need this single crystal. If it is a polycrystal, then this technique is failed. Okay, so we need the single crystal, and we need the source of X-ray as a white X-ray, or which is also called as the polychromatic X-ray, and the X-ray range is from 0.2 angstrom to 2 angstrom unit. Okay, so that means 0.2 to 2 angstrom, they are mixing and they produce a white X-ray. So that means that white X-ray is nothing but a polychromatic X-ray. Okay, not a monochromatic, polychromatic. So by performing this experiment, we need a single crystal, we need a polychromatic source, and the lambda is variable and the angle is fixed. Okay, lambda angle, it is the part of Bragg's equation, like 2d sine theta is equal to n lambda. So lambda is variable, and from the sine theta of theta is fixed. but it gives only information of orientation and symmetry of the crystal, but not give the total idea of the symmetry of structure of crystal. Secondly, in the form of rotating crystal method, the rotating crystal method give the idea of lattice constant. Then uh, by using this rotating crystal method, you may know about the structure of your material, but there is a one drawback, that is you only describe the single crystal. If it is a polycrystal, then this method is failed. Okay. So here lambda is fixed, that is why it is a monochromatic. Okay. But theta is variable. Theta is variable of the Bragg's equation. 2d sine theta is equal to n lambda. Of this lambda, the wavelength is fixed. You need the monochromatic wave. Next is powder diffraction technique. So powder diffraction technique is currently used to describe the atom, because this is a very good technique, because this technique not only gives about the symmetry or orientation, but also gives the lattice parameter. Here it is also give the idea about the single crystal as well as the polycrystal, because in the nature the maximum crystal they are not a single crystal, they are a polycrystal. So in lab, when you synthesis your material, so many time your material is also a polycrystal, not a single crystal. Okay. So this instrument is useful for the polycrystalline material, so that is why it is a more powerful technique. And here also lambda is fixed, that means it is a monochromatic. Wavelength is fixed, either 1.54 for copper, 54 angstrom for copper, and theta is variable. So this is the brief idea of three different technique to determine the X-ray, determine the or study the crystallography or crystal. So this is the typical pattern of X-ray diffraction. So using the machine that I am show in the earlier slide, using the machine we get the theta value as well as the intensity. That intensity is the arbitrary unit, keep it in mind. So many people there find the 1000, 2000, 3000, 4000, or sometimes they only indicate 10, 20, 30, 40, 50. So this is none of the matter. So this is actually arbitrary units in the form, the intensity give the arbitrary unit, and this is the in x-axis they recorded the 2 theta position. So this gives the position of the peaks, and here is the intensity of the peaks. Okay. So this type of structure it is produced from the X-ray diffraction machine. Actually they gives in the form of 2 theta in the Excel sheet, in the form of 2 theta and intensity count or intensity percentage. So you can draw in the Excel sheet, you will find this type of graph. Okay. So this graph indicating here the some peaks are high intense, some peaks are low intense, some peaks are merged, some are peaks having the full width and half maximum width is different. So this intensity, width, and some this mixture of some two peaks, they will tell so many things or clear so many idea about your material. So we'll discuss one by one. The first thing is the peak position. Peak position means this 2 theta position gives the idea of peak position. Here is the lower angle position, here is the higher angle positions. So 20 is the lower angle in this case and 60 is the higher angle. So applying this 2D sin theta is equal to n lambda condition, I may discuss about the 2D crystal. This is 110 plane, this is 110 plane also, this is 230 plane, and this is 010 planes. Okay. So this is the arrangements of atoms. This distance between this atom to atom is an interatomic distance, and this distance is called as d. So this distance is not only possible to count from this atom to this atom, this distance is possible to count this atom to this atom, this to this, and this plane to this plane also. So there is a number of direction to measure the crystallographic line or crystallographic plane in a 2D as well as 3D. In 3D they are indicating as a Miller indices, but in 2D there is a indices plane. So this indices plane of the distance between this indices plane is different in a different orientation and different direction. So this plane means I am talking about this line, actually plane, and the distance between this first line and the second line, it is called as d. So this d is the higher in case, and this distance between this line and this line is lower, means here is the greatest d value and here is the smallest d value. So if d is large or greater, then sine theta is equal to, I can also say, n lambda, and this 2d is going in the denominator. So this sine theta is equal to n lambda by 2. If sine theta is equal to, I can say, n lambda by 2d, and if the d value is large, that means nl value is, or lambda value is small. If the lambda is small, that means theta is also small. That means that concluded that, or statement that if the d value is larger, then the peak is shifted to the lower value of 2 theta position, like this. That means if this is the largest d value, then this peak is the peak for the plane of 0, 1, 0. So here we always try to incident the waves as a manner, incident the X-ray as a manner of increase the probability of rightly oriented plane, such that at right oriented plane it follow the Bragg's law, and when it follow the Bragg's law, the diffraction pattern is produced coherently. Okay, then and only then you get the peaks. Okay. So in this slide, the motto is to say the larger is the d value, lower is the 2 theta position, and smaller is the d value, the higher is the 2 theta position. That means if this is the d value is lower, then this plane or this peak is for this plane of 2, 3, 0. Okay, because here d value is small. If d is small, then sine theta is larger, means angle theta is larger. So that is why it is shifted toward the higher value of 2 theta. Now next is to discuss about the peak intensity. How many types of, or how many peaks are available in the crystal. So here I would like to discuss with the two examples. The first example is for body centered cubic, and second example is for the face centered cubic. So you may observe, if you observe carefully, this body centered cubic having 1, 2, 3, 4, 5, 6, 7, 8, 9 peaks. Okay, and this face centered cubic having the 1, 2, 3, 4, 5, 6, 7 peaks. The 2 peaks is less as compared to the body centered. Okay, so that means this atom, this crystal, the number of atom is this 8 corners having the 8 atoms divided by 8. So there is a one atom in the corner atom, they are distributed, and one atom in the center. So the total number of atom in this body center is 2. Okay, and the peaks is 9. And in the face center, this corner is 1 and 6 faces is half. One atom is sharing the half of the atom in the one face, and remaining half to the nearest neighboring face. That means in face centered cubic cell, there are 4 atoms is there. So if there is a 4 atom, the peaks is 7. If there is a 2 atom, the peaks is 9. That means if the atomic density is small, then the peaks are reflected planes get larger. If the atomic density is larger, then the reflected peaks are smaller. Okay. So here I would like to discuss with the two cases. This is the simple cubic, and this is also simple cube. In the case 1 and in the case 2, I just add one atom. Okay. So this atom is sharing half portion of the atom to this face and another half to the nearest neighboring unit cell, and this is also half portion sharing to this unit cell of this face, and remaining half is sharing to the bottom of the nearest image cell. That means the total contribution of added atom is 1 in this simple cubic, but the position is simply different as compared to this case 2. In case 2, I am also added only one atom in the simple cube, but I put this atom in the center of the body. But here I put the atom in the top and bottom of the face. Okay. So I added one atom to each simple cubic. Now see what is the difference that is occurring in the structure or diffraction pattern. So this is for the case 1, I added one atom of half portion at the face and half portion at the bottom. So this is the ray which is coming from the X-ray machine, and this ray are incident, and this is the reflected from here, and they produce a scattered X-ray. And ray 2 which is also coming from there, and this is scattered from this plane and reflected from this plane, and they produce a scattering beam. Path difference is lambda between this ray 1 and ray 2. Then they produce a constructive interference pattern. That means here it is follow the Bragg's condition. The Bragg's condition is very important for each and every case. Only the constructive interference pattern is possible only when they satisfy the equation 2d sin theta is equal to n lambda. Okay, means left hand side is equal to right hand side of the Bragg's equation. Then and only then it is possible to create a constructive interference pattern, otherwise not. So let's see for the example of body centered. Okay, so this is ray 1 which is reflected from this plane like this, and ray 2 which is again reflected from this plane like this, but ray 3 which is reflected from this atom, and they produce like this type of scattering beam. So there is a path difference between the ray 1 and ray 2. Ray 3 is lambda by 2 if it is a for the case of case 1. If this is a lambda, path difference is lambda, then in this case this path difference is lambda by 2, because this trough and crust are opposite to each other. Here trough and trough are match, and the crust and crust is also match, but here trough and crust get opposite to each other. That means they are destroy each other. That means no X-ray is recorded. No X-rays is recorded. There is a no intensity. So that means the intensity of the peak intensity is purely depends on the position of atomic density. So that means if the atom position of atom is changed in a plane, then there is a probability of getting the constructive interference is less. Okay, and the Bragg's condition is also not satisfied if the position of the atom is changes from this phase to another. Okay, so likewise there is so many planes in a crystal, like 110 plane, 311 plane, 200 plane, 411 plane. So many numbers of planes are there. Okay, so these are the allotted reflections from the simple cubic, face centered and the body center. If you observe the h square, k square and l square value, if this is for the simple cubic 103, this is nothing but a h is 1, k is 0, l is 0. If they put the value of h is 1 in here, then that is 1 square 1, k is means 0 square 0 and 0. If you add this 1 square plus 0 square plus 0 square, you will get 1. Here 1 square plus 1 square plus 0, that means 2. Likewise, for the simple cubic, the reflection peak which is allotted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, but in the face centered cubic 1, 2, 3, 4, 5, 6, 7, 8 only, and in the BCC means body centered, atomic density is more as compared to FCC. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 allotted reflection peaks planes are allotted. So that means if the atomic density is small, the allotted reflection peaks is larger. If the atomic density is larger, then the allotted reflection are smaller. Okay, so that means simple cube shows all the peaks, and limited peaks are visible in the BCC and FCC. That means the overall intensity of the peak is because of the superposition of all the constructive and destructive contributions, which is obviously guided by the position of atom. That means this reflection is totally depends on the position of atoms only. But in case of this allowed deflection plane, this 7 and 15 is missing because cannot be expressed in terms of h square, k square, l square. So keep this the key parameter in your mind. So 7 and 15 of the h square and k square, k square plus l square is not possible. So this reflection are not possible. Now in this typical XRD pattern, you may also observe the width of the peak. So width of the peak is also depends on the crystallite size and the lattice strain. If the size is decrease or increase, the peak width also affected. If the strain is decrease or increase, the peak is shifted towards higher angle, or either sometime it is shifted towards the lower angle. That means peak width is depends on crystallite size and lattice strain. Okay. So when you synthesize your material in a lab, so you may say your material is a homogeneous, but not actually all material is a homogeneous, because this is the internal structure of material. It is looks like a homogeneous but not 100% homogeneous. There is a little orientation of this crystal is different, orientation of this crystal is different, orientation of this crystal is different. That means no material, not every material is homogeneous and continuous. Okay, it is made up of some very small parts of parts, and each part is diffracted X-ray at slightly different angle. Okay, so suppose from this XRD, if you put this material, this entire crystal or entire material in a XRD machine, so this crystal diffracted X-ray with a different angle, this crystal diffracted X-ray with a different angle. Okay, so this material may be divided into three parts. One is for the large crystal, second is for the small crystal, and third is for the very small crystal. If your crystalline size is very small, then what happened, and if it is a large, then what happened, that I am going to discuss here. See, this is a large crystal. Diffraction angle from this diffracted X-ray is fixed, so that is why they are just diffracted from the peculiar or fixed angle. So that is why they gives the sharp X-ray peak. So this peak is very sharp. So it is possible in the case of when the crystal is very large, because at large crystal the diffraction angle is fixed. Now I am talking about the small size crystal. So this crystal having the different orientation, this second middle crystal having the different orientation, and this third crystal is also having the different orientation. So this different orientation makes a different crystallographic angle, but this orientation is not so much difference. Okay, so that is why the diffraction angle is not too much difference. Okay, if it is suppose 39 point, or it is called as 38.5, the diffracted angle is 38.5 for this first crystal, then it is maybe 38.6, and it is maybe 38.3. So this 5, 3 and 6, they produce just little of width of this crystal is just little bit larger as compared to the large crystal, because it is a very sharp peak, and this peak is little broadened. Okay, now the main part, that is the very small. If it is a very small crystal, then there is a number of crystals, they are divided into, means the material are divided into so many crystalline size, and this small crystal is oriented in a different angle or different orientation direction, and this different orientation direction of all this crystal means there is a concept of surface to volume ratio also. Okay, so if it is a nanomaterial, then surface to volume ratio increases like this. If it is a nanomaterial, then the very small crystalline size ratio is getting increasing and increasing. That means this orientation of this atom, this crystal is different. That means diffraction angle is also different for this each and every crystal. So this create a large broad peak area. See, as compared to this one is a very sharp, this one is little broaded peak, and this one is a large broaded peak. That means if the crystalline size is small, you get the large broad peak. If the crystalline size is moderate, you will get the moderate broad peak, and if the crystalline size is larger, then you get the sharp peak. So this is the first observation you can observe from the Xray data. So this is the last part of this video lecture. This is the peak shifting, and this is also very important point to be discussed, I think. Friends, so many people nowadays they are try to adopt your material with a different concentration, and you can vary your material with x is equal to 0 to 1, means this is the concentration level 0 to 1, 0 to 0 0.1, 0 0.2, 0 0.3. So in this example there are four XRD pattern of the same material with a different concentration, and if I zoom this area, means highest intensity peak, then I can find this intensity versus 2 theta. This is for x is equal to 0, black color curve indicating. This red color indicating here, it is x is equal to 0 0.1, then it is 0 0.2, and this doping concentration is 0 0.3. This peak is here at some particular peculiar angle, and this peak is shifted towards the lower theta value position, and this peak is also shifted to the lower theta position, and this peak also shifted to the lower theta position. Friends, sometimes some peaks are shifted to and fro this natural peak, means sometime it is shifted to the lower theta position, sometime it is shifted to the higher theta position. So why it is happening in a crystal or X-ray diffraction pattern? It is because of the strain. Listen it carefully. It is because of the strain that this peak are shifted either towards the lower theta value or either towards the higher theta value. Okay. So this is the natural lattice size, or if there is a no strain is applied, that means this is suppose a d value, that means interatomic distance of the crystal. If suppose this is a crystal, then there is a one atom, this is another atom, these atoms are periodically arranged, and these lines are the crystalline planes. So the distance between these two lines, which I called here, it is a interatomic distance. If there is a no strain is applied, then this is the natural lattice size, means there is a no increase or decrease in lattice size. So this is the natural peak or scattered peak which is recorded by the diffraction pattern of the X-ray. So when I apply the uniform strain, that strain in the form of uniform compression, that means I am applying force from this boundary to this boundary, that means the d value of this, means interatomic distance get reduced. So you know, using the earlier slide I already discussed about the Bragg's equation, 2d sin theta is equal to n lambda. If d is decreases, if d is decreases, means d value is small for the smaller d value, larger is the peak position, means for the small d value the peak is shifted to the larger theta position, and for the larger d value the peak is shifted to the smaller theta position. So here it is a compression, that means due to the compression the d value or the distance between this interatomic plane is decreases. If the distance between the interatomic plane decreases, means d value decreases, and by applying the Bragg's condition, Bragg's law, if d value decreases, then the peak is shifted towards the higher theta value from this right. Now it is a uniform compression. Compression means they are stretched from this boundary to this boundary, that means the d value is increased. For the larger d value, the peak is shifted to the lower theta position. So this is due to the strain. So in this figure, this is happening due to the, they are shifted towards the left side, means lower theta value. That means there is a larger d value, means larger d value means there is a strain which is applied in the form of, not in the form of compression but in the form of expansion. Okay. And what happened when there is a non-uniform strain in the material? That means this material get confused, either it will get up, down, or left, right, they are compressed or they expand itself. So that type of strain is called as non-uniform strain. When is it is a non-uniform strain, then this peak not shifted towards the lower theta value as well as not shifted toward the higher theta value. They only increase the width of the peak. That means the full width and a half maximum get increased. And using this curve, Gaussian curve fitting, they are giving or giving this type of curve. And because of this type of curve, when there is a non-uniform strain is applied, the full width and half maxima get increases, so peaks get broader. So these are the reason for peak shifting and peak broadening. Okay, so I would like to stop here. The next lecture will be continue with the live demonstration of the data which is coming from the machine, that I am going to live demonstration, and I will record my screen of this laptop and I will share with you. Thank you for watching this video lecture with very patiently. Once again, I would like to say thank you each and everyone. If you have any questions, please email me on my email ID sarkariresearch@gmail.com. Thank you very much.